Hi, welcome to this second part of a video about how you can customize text extraction and chunking of your documents using kernel memory. In the previous video, we saw how to use Llama Cloud parsing services to extract text with a contextual prompt from your documents. And now we're gonna look at another advantage that you have if you follow this approach in extracting text from your document, and it is a better chunking of your documents. So when we talk about chunking, it means that a document has long part of text, and since we are gonna use vector search and we wanna reduce the number of tokens we are passing to a large language model to answer the user question, if we have a large document, we usually segment the text into small pieces of segment, and usually this is done using a fixed number of tokens. So as an example, 500 tokens. And that has a problem because when you extract text from a structured document that has chapters, paragraph, and so on, using a fixed number of tokens usually gives not the best result because it's probably you can break a paragraph or you can take things that are not related together. So it can be problematic. So if you instead extract text with the use of a large language model, you can instruct, as we see in the previous video, the large language model to use a specific structure in output. Let's see how we can create a custom chunker that takes advantage of this fact. Okay, we ended the previous video having the text that is extracted with a fixed structure. We asked to the large language model, we asked to the Llama Cloud parse services to extract from a technical document a series of answer and question that we can fed to a RAG system that should help a call center to solve problem of the user. And given this, we asked to the service to extract question and answer and divide each question and each answer with a specific series of token like 4 dashes. And this is good because we can now create a custom chunker in kernel memory that takes advantage of this specific format of the extracted text. Now, we have in kernel memory, we have not a specific interface for text splitter. Instead, we have a generic interface called High Pipeline Step Handler. This is an interface of one step of a pipeline. And from the point of view of kernel memory, when you ingest a document into your system, this document follows a sequence of step handler. So if you want to chunk the document with a custom strategy, you need to create one step handler that does this operation. Actually, you need to implement an invoke async generic function. And this function simply can examine what we already have for this document and create new part of this document. So as an example, the first check is if the pipeline currently has no files, we have nothing to do because we are building a chunker, a splitter that is capable of extracting pieces of text based on the previous structure. So if we have no file, we have nothing to do. Then we need to take the context and we can iterate in all the pipeline files, and we just need to examine all the files that we have in the pipeline to see if we already have an extracted text that can be chunked. Now, when we look at all the generated file in a specific uploaded generated file, we are examining all generated file. And first of all, the pipeline does already a good job checking if the pipeline already processed this file. And this is because if for some reason the pipeline get interrupted and restart again, and we lose all the context we have in memory, the pipeline stored into a database, the step we are reached and which kind of work each step has done. So if we have already processed by this pipeline means that the file was already processed. We don't need to process again. And then we do another check. And the idea is if the artifact type, so we are using an artifact, so we are not using the original file of the user. We are using an artifact, something that was produced by a previous step in the pipeline. And we are looking for artifact of a specific type. It is extracted text because we are creating a chunker. So it's a piece of code that takes the original text and subdivides into chunks. Then we are in presence of a file that was an extracted text. So first of all, we are getting the content in a binary data. And we start telling that we will have a partition MIME type made of markdown. And that is because we know that we are using this specific chunker only with the previous example. So when we already know that the text extracted was extracted by Llama Cloud parse with a custom prompt. So then we can switch for the MIME type. And so we are going to say if the MIME type of the file is indeed a markdown, we're going to create a simple string builder, and we are using a string reader, and we're going to read the content of the file until we find the specific structure. I mean, we have answer and the answer and the question and the answer. In each couple is subdivided by 4 dashes. Now, that is a very simple code. We, as you can see, we check for the presence of 4 or 3 dashes, and if we find this is a separator. This is a separator line. So if we found a separator line, we will add a segment. So we will create a specific object of kernel memory that is a segment, and will be clear the string builder. So we are going to build the next segment. So in this situation, we are using the kernel memory structure. So we have a chunk in which we expect to have text. So both the question and the answer are in the same chunk. If you don't want to use kernel memory, you want to use your code, you could parse and you could separate also question and answer. So you can maybe ingest in a database differently question and answer. For this example, I just only want you to know that the standard technique is if you have a service like Llama Cloud, in which you can specify the output format, it is probably good to write a custom parser, a custom chunker that can take advantage of this format. If you're interested in more detail about how to generate chunk, you can look at the code, but basically you create another destination file. So the kernel memory works using a pipeline in which you ingest the original file, and each step of the handler produce other files until you have finished all the step and you have a set of files that can be taken and indexed in your vector database or in your Elasticsearch or other databases that are capable of using BM25 or TF-IDF keyword search. So that's pretty much simple, and that's pretty much standard code. And as you can see, for the ID of the chunk, I'm using a new guide because each chunk has a different ID. So no rocket science. And let's see what is the result of this particular chunker. Now, if we look at as an example at the partition 2txt is one of the partition, you see the text is question and answer. This gives me a really better results because now I'm able to index in my database something that is coherent. So we have all pieces of text where each piece of text is a question and a relative answer. So I think it is much more better approach than using a standard chunker that has a fixed size in tokens. And you can do even a more good job, and that's because you can write a customized step that calculate the vector for this piece of text, because you can use a structure that parse this output and use only the question when you calculate the embedding of the record, because probably we are not interested in the embedding of the answer, but we are interested in the embedding of the function of the question. But that's as simple as the code you already seen. So write another text handler that know that each partition is made in this specific structure. Look for the ** answer, split the string, and calculate the vector only for the question part. So as you can see, kernel memory is very, very flexible and let you do a lot of small personalization that allows you to customize and to bring your specific data, your specific RAG system into production using custom extraction, custom chunker, and so on. Just a reminder, to create your own pipeline, you simply create all your partition handler. And in this situation, here is my new markdown partition. Oh, sorry, this one. So once you create all of your partition handler, you can create a pipeline. A pipeline is nothing else than an orchestrator that is prepare new document upload. So you give an index in kernel memory in which you want to store the document. You give a file name on the document. Maybe you give a document ID, that's a unique identifier. Usually it consists of the file name if you're indexing a folder in your system. But if document is contained in the database, it can be the ID of the database. This should be a unique index. It is the unique index of the document. Then you had add upload file, where you really specify to kernel memory which is the binary file that contains your data. And you have a series of then, and as you can see, it's a pipeline composed of sequence of steps. So in this example, I have the extract that use Llama Cloud. Then I have my markdown partition, and it is the class that we saw in this video, and it's capable of taking into account the fact that extractor test has a specific structure. Then you have a generic embedding, and that is, we will see in the next video how we can customize the general embedding. And then we have a standard save record in which the records are saved in the database. And then you will proceed as we see in the previous example. We will simply go in specifying the custom prompt we have, we should use for this database. Then we build the pipeline and we execute the pipeline. So it's very few lines of code. So in the end, kernel memory simplify a lot the operation of customization, of personalizing your ingestion pipeline, where the ingestion pipeline is simply a pipeline that you can build by step using sequential series of steps. You give to the pipeline the binary document you want to analyze, then you specify the step, and you can change the steps for each document. So this allows you to have a specific way of extracting text based on the document, and it can be based on the type of the document, or it can be based from where you keep the document. So you can say, this kind of document, I will do this analysis. This other kind of document, maybe old PDF, but they come from a different source, so we know we need to analyze in a different way. Not only the very same document, like this one in the example, that is a manual for a vacuum robot, vacuum cleaner, can be indexed several times in different index. Maybe you index in this index using this kind of structure that extract question and answer, and is for your call center. And then the same file can be indexed in a completely different way for a technician that want to have an idea of maybe the images that are contained. So it is normal in a RAG system to create different index. Each one is get queried based by question by different person. So you can have same document in different index, and based on person that makes the query, or based on the type of query you are doing, the system is going to route the question into the right index where the document is indexed in a specific way. And that is the way you can personalize your RAG system, and it can give you a very good result when you go in production. Bye-bye, I'm waiting you for the next video in which I show you how you can customize the third part of this pipeline, the embedding generator.